All right, just going through some problems that are in the data and related rates category. On this first problem, you can see that we've got a table of data, so data area. Notice this is a calculator problem. It says a zoo sponsored a one-day contest to name a new baby elephant. Zoo visitors deposited entries in a special box between noon, which is time equals 0, and 8 p.m., which is time equals 8. The number of entries in the box, t, hours after noon, is modeled by a differential function, e. For 0 is less than or equal to t is less than or equal to 8. Values of e of t in hundreds of entries, so that second row is hundreds of entries, at various times t are shown in the table above. Part A, use the data in the table to approximate the rate in hundreds of entries per hour at which entries are being deposited at time equals 6. Show the computation that leads to your answer. So we are estimating right here between what we have in the table, which is at time equals 5 and time equals 7. So to use that, we would do the slope of the secant line, or the function's e of 7 minus e of 5, so we're sandwiching that times 6 over 7 minus 5. So grabbing those values from the table, we'd have 21 minus 13, which would be 8, divided by 2 is 4, and again this is in hundreds of entries per hour, so that's 4, or 400 entries per hour. Part B is a trapezoidal sum, so thinking trapezoids here, connecting those values, with 4 subintervals given by the table to approximate the value of, and notice the 1/8 in front of that. So the 1/8 we will hold on to, and then to do the trapezoid part of it, that's going to do the integral part. So I'm going to do my trapezoids inside of here, so we'll just do our trapezoid formula, 1/2 the height, and the height, if I were to look at this first trapezoid, so my first trapezoid is going to be those values right there. Remember, the height is going to be the distance between our bases, or the distance between our variable here, which would be 2, and then our two bases are going to be the two function values on either end of that, so 0 plus 4, base 1 plus base 2. And we're going to do that for each of our trapezoids across here, so 1/2, and then we do our next height, which would be between those two, a height of 3, and again the two bases are the two function values, so 4 plus 13 plus 1/2. Our next height would be between 5 and 7, so a height of 2, and our two bases would be 13 and 21. And our final trapezoid has a height of 1, and our bases are 21 and 23. So this is, again, a calculator problem, so I'm going to type all that into my calculator. I went ahead and did that, and I got 171 over 16, which is approximately 10.688. And again, the problem can kind of help us, but this one did not say. It says using correct units. So part of this one is making sure that we are labeling this. Now, E of t is our hundreds of entries, and we took the integral of that, and then we divided by 8, which was our difference in the time. And so this would be an average. It's an average of this function is what we're looking at over that interval. And E of t is in hundreds of entries. So we would have an average of 10.688 hundred entries. Over that span from time equals 0 to time equals 8. And that's our average number of entries on that span. All right, part C asks us at 8 p.m. the volunteers begin to process the entries, meaning they remove them from the where they were turned in. The process entries at a rate of P of t, which is t cubed, minus 30t squared, plus 298t, minus 976 100 entries per hour. And that started at time equals 8 to time equals 12. According to the model, how many entries would not been processed by midnight? Okay, so first of all, what I did is I looked at how many, I went back to the table, how many entries did we have at time equals 8? So that would be E of 8, which is 23. So at time equals 8, or E of 8, we had 2,300 entries. And what we want to do then is, okay, so that's what we're at, first of all, starting at 8 p.m. And then there we stop at getting more entries. So we're going to stay static at 23, but we're going to subtract what is being processed. Well, what they gave us for the processing is the rate at which they are being processed, which is P of T. So to find out how many are actually getting processed in that time, we would do the integral of P of T. And our timing on this is going to start at 8 o'clock and go until midnight, which is 12, because I want to know how much is left over, and that's why we're subtracting it from the 23. So as we look at that 23 minus how many are processed during that time, our answer ends up being 7. And so the question was, how many entries had not been processed by midnight? And remember what that's representing, 700 entries. According to the model from Part C, what time were the entries being processed most quickly? And so again, for our most quickly, we'd be looking at our maximum of the processing rate function. So if I look at the max, if I want the maximum of P of T, I would check, first of all, the ends of the interval, which would be from time equals 8 to time equals 12. But I would also check the critical points of its derivative. So we're going to check out the critical points of P prime. So I found P prime, which would be just using our power rule here. So 3t squared minus 60t plus 298. I use my calculator at this point, and I set that equal to 0. Well, what I did is I graphed it and used my 0 function. So I graphed that and I found my zeros, and it told me, and I set my window from the time that this is happening. Remember that this function is from time equals 8 to time equals 12. So I set my window to 8 to 12, and I found out it had zeros during that time at 2 different places, at 9.184 and at 10.816. So then I can go to a table here and check out, all of those values. That should be a time. And we start with the ends of the interval at 8 and at 12, and then at any of the critical points we found, which was 9.184 and 10.816. Now those are the critical points. We find those from the derivative, but ultimately we are trying to find the maximum, right? The most quickly of our rate formula, which is P of T. So I would go plug these into P of T, and these were the values I got. 0, 5.089, 2.911, and 8. So then scanning through there, finding our largest value, they are being processed most quickly. At time equals, and of those values, 8 was our highest, so at time equals 12 hours. Now, it does say it at the end, justify your answer, but guys, all my work is that justification, that I found the critical points, that I identified of those, what values I needed to test, and doing that. So finding the actual values here for all of these points that I recognize could be the location of those maximums, that's all my justification. All right, so then just kind of talking through some multiple choice problems that would involve tables of data. This next one, we've got a table 2, 5, 7, 8, and 10, 30, 40, 20. Function f is continuous on the closed interval from 2 to 8, has values that are given in the table, use subintervals of 2 to 5, 5 to 7, and 7 to 8, and the trapezoidal approximation. So again, our trapezoidal approximation is going to use that trapezoid formula, 1/2 our height, and remember the height is going to be the distance distance between your independent variables, so between 2 and 5. So our height would be 3, and then our bases are the function values at those locations, so plus 10 plus 30. That would be our first trapezoid. That's the one for the interval from 2 to 5. Our next trapezoid from 5 to 7 would have a height of 2 and function values or bases of our trapezoids of 30 and 40. And our last one from 7 to 8 would have a height of 1 and function values or bases of that trapezoid of 40 and 20. So then I kind of evaluated all of that. Let's see, this would be 60, 2 to 70, and 30, which would give us a total of C, 160. All right, the next one, the same function f is given above. The function's rate is decreasing. So the rate, remember, if we're looking at a function's rate, the rate is going to be the derivative. So the derivative is decreasing fastest at what value of f double prime? So if I want f prime to be decreasing, and this is the key on this one, if f prime is decreasing, that means that f double prime has to be some negative value. And so that actually tells me exactly what we're looking for on this. In order for this to be decreasing, it doesn't even matter if it's the fastest, slowest when it's decreasing, but to be decreasing at all, your second derivative would have to be negative, and there's only one option up here that gives us a second derivative that is negative. So that would be at negative 20. All right, on our next one, we are given this function is a differentiable function on the interval from 0 to 2. Find the derivative, and we've got an inverse function. And so our big key on inverses is remember that a function and its inverse, the x and y values flip-flop. And so when they tell us that we're looking at x equals 1/2, what we're looking at there, so they're asking us what, let's see if I can write this in here. What is the derivative of f inverse of 1/2? They're asking us for that derivative. So let's talk about that real quick. If I were to be looking at the original function, f of x, then for f inverse to be evaluated at 1/2, remember that the x and y's flip-flop, right? So if it's 1/2 for the x value in the inverse, that means it would have been an answer of 1/2 or a y value in the original function. So I came up here and I said, okay, which one has a y value or a function value of 1/2? And that would have been a original x value of 3/2. Why do I care about that? Well, then the derivative of each of these are reciprocals of each other. So the derivative of the inverse at 1/2 is the reciprocal of the derivative of the function at 3/2. So if we find that function at 3/2, its derivative is negative 1/2, which means the inverse's derivative at 1/2 would be the reciprocal of that, which is negative 2. So scanning through now what I've written all over, that would be option B. All right, and then using again the table above and the fact that the derivative is continuous from 0 to 2, we are supposed to find the integral from 0 to 2 of the inverse. So a reminder on our fundamental theorem of calculus is that the integral can be evaluated by taking the antiderivative. Well, the antiderivative of f prime would be f of x, and taking that of the top value minus the bottom value, and those values we can get from our table up here. That f of 2 is here, 3/2. F of 0 is here, which is 1, and 3/2 minus 1 would be 1/2. And that is option D. Okay, And another one here, the radius of a circle is decreasing at a constant rate of 0.1 centimeters per second. Ooh, this one is a tricky one in the wording here, and we're going to come back to this. In terms of the circumference, what is the rate of change of the area of the circle in square centimeters per second? So first of all, we've got a rate of change of our radius over time. They tell us the rate of a circle is decreasing, the radius of a circle, sorry, is decreasing at a constant rate of 0.1. So if it is decreasing, that rate is a negative 0.1 centimeters per second. And then they talk about the area, and they want to talk about what is the rate of change of the area. Well, I know what the area formula is for a circle, and that is pi r squared. But the question is, what is the rate of change of the area? So the rate of change would be dA dt. So if I'm going to do that, I've got to take the derivative of the entire function. And so what we're doing right now is talking about the derivative of the right-hand side here. And the derivative of pi r squared, now remember, pi is just a constant. And so when I take the derivative, that constant is just along for the ride. And so the derivative of r squared is just your power rule, 2r. So I'm going to write that as 2 pi r. 2r is the derivative of r squared. But r is not t, so we then have to also show taking the derivative of any variable that is not what variable we are doing this with respect to. So then we would multiply this by dr dt. So now let's go back to what I said we were going to address in the directions, and it said in terms of the circumference C. Well, C is 2 pi r. So I can replace this 2 pi r with C. Just doing a little substitution here because they wanted it in terms of the circumference. But I also know what the derivative or the rate of change of the radius is. And so then I can plug in this negative 0.1. To get the rate of change of the area in terms of the circumference, which would be option B. All right, and finally, again, a rate of change problem here. It says in the triangle shown above, if theta increases at a constant rate of 3 radians per minute, at what rate is x increasing in units per minute when x equals 3 units? So looking at this picture, first of all, if you remember when we were dealing with rates of change, what we wanted to do is write an equation that related all of the pieces of information together in our picture. And one of those that we can do in this one, if I'm looking at this, we've got the angle theta, we've got our side length x, and we've got our side length 5. And 5 is a constant and not changing, but x and theta will both change. So I will leave them as x and theta for the time being as I write this function. But from theta, x is opposite, 5 is the hypotenuse, and so I can write a trig function that says the sine of theta equals x over 5. And we are looking at this, at what rate is x increasing in units per minute when x equals 3. So eventually on this, we would look at this, and it does also tell us one other piece of information, and that is that d theta, if theta is increasing at a constant rate, so the change in theta increasing, so positive, of 3 radians per minute. So eventually we know that d theta dt is going to be 3. Okay, so as we're looking at this, first of all, if that's my function that relates all of those variables together, to start inserting in our rates of change, I would want to look at the derivative of this function. So the derivative of that, derivative of sine is cosine, and then derivative of the inner function would be d theta dt. So that would be my full derivative of the left-hand side. Now I can think of x over 5 as 1/5 x here, and the derivative of that would be 1/5. And then the derivative of x is dx dt. Well, at what rate is x increasing? That's what they're asking us to solve for. And they ask us to do this specifically when x equals 3. Now that's the key on this one, when x equals 3. Okay, well, if x is specifically going to be 3, if I draw that in our picture here, I know a little bit more about this triangle. That is a 3, 4, 5 right triangle based on my Pythagorean theorem. And the reason I show you that is because then I can figure out what the cosine of theta is. Cosine of theta is theta is adjacent over hypotenuse, and so by substitution I can replace cosine of theta with 4/5. I can replace d theta dt, that's over here, d theta dt equals 3, so I can replace d theta dt with 3, and we are then eventually supposed to solve this for dx dt, which means I would multiply by 5. Okay, so then multiplying all of that together, straight across the top, straight across the bottom, it looks like we would have a rate of 12 units per minute. All right, from here you guys are going to work on your data and related rates review worksheet, and we will discuss at our next Zoom meeting.